Covalent substances can be simple molecular covalent or giant covalent. Ammonia is a simple molecular covalent substance, which is most likely the set of properties for ammonia. So simple molecules basically have very low boiling points and melting points, and they cannot conduct electricity. So you're just looking for anything that fits that bill. So here, lowest melting point, lower boiling point, and doesn't conduct electricity is the only one. This one would be a giant covalent structure, and this one would be a giant ionic lattice, because this one has a high melting point but doesn't conduct electricity. This one has a high melting point but does conduct electricity. Right. Ammonia NH3 is made by reacting nitrogen and hydrogen. Write the balanced equation for this. So here we have, Here we have nitrogen and hydrogen, and they're reacting to make ammonia. So what I do as usual, I draw my line where the arrow is, and I write the elements on each side in the same order: nitrogen, hydrogen, nitrogen, hydrogen, and I count them up. 2 nitrogen, 2 hydrogen on this side, 1 nitrogen. Remember that the 3 only applies to the capital letter it's in front of, and 3 hydrogen. So that's what we're starting off with. And we want to increase, obviously, the amount of nitrogen on this side, but hydrogen on this side. So let's start off one at a time. So I'm going to start off by writing 2 here. By writing 2 here, this changes to 2, and this will be 6 lots of hydrogen, 6 here. So now that is balanced, but this one isn't. So now I need to make sure there's 6 hydrogen on this side. So there's 2 here. So if what can I multiply 2 by to get 6? 3. So by putting 3 hydrogen here and 2 here, we end up with 6 here. 3 times 2 is 6. So that is now balanced. 6, 6, 2, 2, balanced. Oxygen O2 is also a simple molecular covalent substance. Draw a dot and cross diagram for the molecule of oxygen. So remember, oxygen is in group 6. It has 6 electrons in its outer shell, and it will require 2 electrons. That means it will share 2 pairs of electrons when it forms a covalent bond. So however many electrons it needs, that's how many pairs it will share. So dot and cross diagram, you must show the crosses on one atom the electrons belonging to one atom and the electrons belonging to the other atom. And you can see they're sharing 2 pairs. So you draw the 2 pairs first, and then these count for both. So this atom here now has 1, 2, 3, 4, and I have to add the extra electrons to make up 8. 5, 6, 7, 8. And this one on this side has 1, 2, 3, 4, because they count for both. They're sharing them. 5, 6, 7, 8. If you struggle with these, you can just remember the 6 or 7 diagrams that you need to remember, and you'll get 2 marks. The higher paper generally favours any diagram which has double bonds or more than 1 bond, so more than 1 pair shared. That will limit how many you have to memorise. Figure 8 shows the arrangement of carbon atoms in diamond, graphene and fullerene. So these are allotropes of carbon, so same, made of the same stuff but arranged differently. Consider these 3 substances. Explain in terms of their structure and bonding, their relative melting points, strengths and ability to conduct electricity. So this is quite a nice easy one because it dictates the structure of what you're going to write. You have to talk about 3 things: melting points compared to each other, their strengths compared to each other, and their ability to conduct electricity, all by referring back to the structure. So, firstly, I think it's important to note that in all structures, carbon atoms form strong single covalent bonds where they share 1 pair of electrons. That's just setting up the structure. Next, let's talk about diamond first. In diamond, each carbon atom bonds with 4 others to form giant covalent structure. So have a look. You can see, imagine it carries on here. Here we go. 1, 2, 3, 4. The ones which are 3 is because they're bonds which are coming out from the diagram, which you can't see. Okay, so that forms a giant covalent structure. So now we're talking about diamond structure. In graphene and fullerene, each carbon atom bonds with 3 others. So have a look here. You can see 1, 2, 3, and here you got 1, 2, 3. So diamond is the only one where the carbon atoms share 4 bonds. So graphene is a giant covalent structure, but fullerene has a molecular structure. So we're just talking about the structure at the moment. So you can see that this is basically a sprawling, look at the way the bonds keep on going here and here and here, but that doesn't happen here. So this is a molecule, but these are giant structures because they continue on and on. And that will affect certain properties about them. So in diamond and graphene, many bonds need to be broken to melt. So in diamond and graphene, because of their giant structure, many bonds need to be broken for them to melt. So we're talking about the relative melting points. So you need a lot of energy, so they have a very high melting point. Fullerene has weak intermolecular forces, so less energy is needed to separate the molecules. So remember, when you're looking at simple molecules, we don't talk about the bonds, many bonds, because there aren't many bonds. We're just talking about the force of attraction between the molecules. We're not talking about electrostatic forces between atoms, and these are very weak. So with simple molecules, you always have lower melting points and boiling points. So fullerene will have a low melting point because it has weak intermolecular forces. So less energy is needed to separate the molecules. So this gives it a low melting point. This is also why graphene and diamond are much stronger than fullerene, because fullerene only has it's a simple molecule, so it has weak intermolecular forces, and also, as I said before, there aren't many bonds. Like that, diamond and graphene are giant structures, they have many bonds which need to be broken. Now in terms of electricity, there are no free electrons in diamond because all the carbon atoms are sharing their 4 possible electron pairs, so it doesn't conduct electricity. But in graphene and fullerene, you have 1 free electron because carbon, which can share 4 pairs, is only sharing 3, leaving 1 spare or free electron. So the presence of these delocalized electrons, these electrons which aren't being used up, means that this electron can move throughout the structure. So they both conduct electricity. However, with fullerene, because there isn't anywhere for this electron to disappear into, you see with this one, the electron can disappear into the structure. Here, it's got nowhere to go. There's nothing inside this sphere, it's hollow, whereas this one would be layers, you see. But here it's hollow. So because of that, it can only conduct across the surface of fullerene. So limited movement electrons make fullerene a poor conductor or a semiconductor. So you can see there's lots to write here, but if you just talk about the forces, intermolecular forces, and you're talking about the number of bonds they share, you should be able to pick up some marks. You wouldn't need to necessarily get all of these points to get 6 marks.